So a very interesting question is this. If you look at all the algorithms that we studied, whether it is insertion sort, whether it is merge sort, whether it is bubble sort, right, or whether it is quick sort, if you take the worst case time complexity, let's talk about the worst case time complexity. The worst case time complexity of all of these algorithms are either order of n log n or order of n square, right? We have not found any algorithm till now that we have studied which has a worst case time complexity of order of n. We have seen best case order of n, but we have never seen an algorithm till now which has a worst case time complexity of order of n. But it makes sense, right? Imagine if I have an algorithm, if I have a sorting algorithm which has a worst case time complexity of order of n, that is surely better than all of these algorithms. Because whether you take any of these algorithms, even for randomized quick sort, right, the worst case is order of n log n. And we know that order of n is better than order of n log n. We already know that, right? And certainly order of n log n is better than order of n square. But the big question here is there some algorithm which can give us a worst case time complexity of order of n? Is it even possible? The big question is it even possible? Or in other words, the question here is it possible to have a linear worst case? That's important, not the best case. Is it possible to have the linear worst case time complexity sorting algorithm? Very valid question. So before we go and answer and discuss some methods or some sorting algorithms which can answer this question, there is a more fundamental question that we can ask. There is a more fundamental question. If you look at all of these sorting algorithms effectively compare numbers, right? They're basically a comparison based sorting algorithms, because if you notice, we are comparing an element ai in the array with other elements aj to decide whether we should move them in all of them, whether it's insertion, merge, bubble or quick, right? In all of these sorting algorithms, in a nutshell, we are basically determining if ai is less than equal to aj or aj is greater than equal to ai. For some ai and aj, which are elements of my matrix A, given a matrix A, for some of these, of course, insertion sort behaves differently from merge sort, which behaves differently to bubble, which is different from quick. But in a nutshell, we have these comparison operators. We are comparing numbers using less than and greater than symbols. So all of these algorithms are actually called comparison based sorting algorithms, right? So all of these are called comparison based sorting algorithms, right? So the big question, the more fundamental question that we can ask here is, can any comparison sorting algorithm, can there be any comparison sorting algorithm? It could be any sorting algorithm, I don't care. Can there be any comparison sorting algorithm which can sort in worst case order of n? Right? Can there be such an algorithm with worst case time complexity of order of n? That is a big question. So I'll try and prove to you that we cannot have. Okay, I'll construct the proof for you very logically, right? It's slightly an involved proof. It's an involved proof. So you got to strap up and you got to follow through with me. Okay, it's a slightly involved proof. It's not a straightforward trivial proof, but it's not complex. Okay, I'll help you here. Let's prove that there cannot be a comparison sorting algorithm whose worst case time complexity is order of n. Okay, let's go through it. Okay, step by step. So I'll construct the proof carefully. Okay, step by step again. Imagine I have an array where I have elements a1, a2, a3, so on and so forth, an. Right? So this is my array of n elements. So this is my array A of n elements. Okay, this is my array of n elements. So we'll just make n equals to 3 because it's easier for us to understand with n equals to 3. But whatever I'm explaining can be extended to any value of n. Okay, so imagine if I have just a 3 element array a1, a2, a3. Okay, a 3 element array. Okay, Now let's look at what all comparisons are possible. Okay, before we go there, your input, because you have three elements, A1, A2, A3, there are many ways in which these numbers, for example, let's assume I have an array of, I have three numbers. I have an array which consists of three numbers, three distinct numbers. Okay, here let's make some assumptions here to make the proof easier. Let's assume AI is not equal to AJ for all I comma j, which means no two numbers here are the same, just to make the math simple. Okay, we can also extend the mathematics even if numbers are simple. Just for simplicity, I'm just assuming that no two numbers are same here. Okay, so either AI is greater than AJ or AI is less than AJ. One of these two is true always. Okay, all these are numbers obviously, so you can compare them. No two numbers are the same. Now let's look it up. If I have three numbers, in how many ways can I arrange? In how many ways can I arrange these three numbers? This is a problem that most of you must have learned in your 10th grade or in your 11th grade, right? This is the problem of permutations. Right? If you have n numbers, in how many ways can you arrange them, or can you order them? Right? In how many ways can you arrange or order them? Let's take an example, right? Imagine if I have three numbers, 1, 2 and 3. No two of them are the same. In how many ways can I arrange them? 1, 2, 3, 1, 3, 2, right? 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. There are 6 ways in which I can organize them. Right? Very simple. And in permutations, right? In the number of ways I can organize them, or in the number of ways I can arrange them, if you have three numbers, is basically 3 factorial. And how do I know this? Imagine I have 3 places where I can place this. I can pick any one number here because all 3 numbers are distinct, right? Here remember, I've assumed that no 2 numbers are the same, right? Because I've assumed that all 3 numbers are distinct, pick any one number. Okay, I have the first position, I can pick in 3 ways. I can either pick 1 here, or 2 here, or 3 here. So I can pick the first number, the first value. Okay, the first value I can pick in 3 ways. If I pick, let's say this number here. Okay, the second number, because this number is already picked, I can't repeat it, right? I can pick the second number in 2 ways, right? And I can pick the third number in 1 way, right? So the total number of ways in which I can arrange these 3 numbers, or I can order these 3 numbers, is basically 3 factorial. If I have 3 numbers, if you have n numbers, the number of ways you can arrange these numbers is n factorial. This is important. Okay, so this is, let's say, statement 1. If you have n numbers, you can arrange these numbers in at most n factorial ways, right? What is 3 factorial? Nothing but 3 into 2 into 1, right? So this is a very important thing. This is the number of ways you can arrange n numbers. Now comes the fun part. Okay, so this is one fact that we have to keep handy, right? Number of ways you can arrange these numbers. Of course, we'll again stick to just 3 numbers example because it's easier for us to understand. Now let's say I want to compare. So let's say I have A1, A2, A3. Let's draw something called as a decision tree. Let's draw something called as a decision tree. I'll explain you what a decision tree is. It's also called as a binary decision tree. Okay, I'll explain you what this is with the example. Okay, imagine I have 3 numbers and I want to compare these numbers. Remember, no 2 numbers are the same. First, I want to compare if A1 is less than A2. There are 2 possibilities, there are 2 possible answers to this. Either it is yes or no, right? Either it can be yes or it can be no. There are only 2 possibilities because we said AI is not equal to AJ for all I comma j. We already said this. So there are only 2 possibilities. Either A1 is less than A2 or A1 is greater than A2. If the answer is yes, see, because let's assume we are given 3 numbers and you want to sort them. First, I can compare A1 with A2, right? Let's assume A1 is less than A2, right? Then I can compare, is A2 less than A3? Okay, I ask this question, is A2 less than A3? There are 2 possible answers here, yes and no. If the answer is yes, right? If the answer is yes, remember, this is called a decision tree Because in this tree-like structure, at every node, so this is called the node of a tree. This is called the node of a tree. At every node, I'm making a decision. Okay, whether A1 is, so I'm asking a question and making a decision. And this is called a binary tree or a binary decision tree because I can go only two ways. There are only two possible answers to this. Either A1 is less than A2 or A1 is not less than A2. There are only two ways. So these are called binary decision trees. A decision tree because at each node I'm making a decision whether it is true or not. And there are only two decisions that I can make. Binary decision trees are very, very popular in machine learning and AI. Right? So there are in machine learning there is a huge area where you learn binary decision trees in a lot of detail. But let's use it for algorithms here. Right? So the moment I know, look at this is the fun part. I know that A1 is less than A2. I also know suppose if I start here, if I'm given three numbers, let's assume I'm given three numbers 1, 2, 3. Okay. Let's say A1 is 1, A2 is 2, A3 is 3. First I check, is A1 less than A2? Yes. Right? Is A2 less than A3? Yes. The moment I know this, I can arrange these three numbers such that then I know for sure that the sorted order is A1, A2, A3. I know that this is the sorted order. This is guaranteed, right? Because A1 is less than A2 and A2 is less than A3. The only sorted order that is possible, given any three numbers, if it satisfies A1 less than A2 and A2 less than A3, then the sorted order is guaranteed to be. The sorted order is guaranteed to be A1, A2, A3. Right? Now imagine if this is no. The moment this is no, what do we know? We know that A1 is less than A2, but A2 is greater than A3. Right? But I don't know anything about the relationship between A1 and A3. Right? Look at this. What am I saying here? I have my A1 here. A1 is less than A2, but my A2 is greater than A3. So my A3 could lie here. Right? My A3 in the number line, my A3 could lie here or my A3 could lie here. So I don't know. So I need to compare my A3 here. So I will compare my A3 with A1. So is A1 less than A3? There are two possible answers here. Yes or no? Now look it up. Now let's see. So now if this is the relationship, okay, if this is the relationship, okay, here what do I know? I know that A1 is less than A2, right? I know A2 is less than A3 and I know A1 is less than A3. The moment this happens, what is your sorted order going to be? A1, A3 and A2. This is what your sorted order is going to be because look at this, right? Very simple, right? Because this satisfies A1 less than A2. Yes, A1 is before A2. A2 is less than A3. Right? No, it is not satisfying that because this is the path that we are going through. Right? And A1 is less than A3. So if you have these, if your arrays, if the elements of your array satisfy these conditions, the final sorted order is going to be this. So given any three numbers, right? So basically what we're doing a bunch of comparisons and deciding the final sorted order through this decision tree. Right? So now let's assume A1 is less than A2, A2 is less than A3, but A2 is not less than A3 and A1 is not less than A3. Then what would be the final sorted order? The final sorted order here would be A3, A1 and A2. Right? A1 less than A2, valid. A2 less than A3, no. A1 less than A3, no. Okay, so this is going to be the final sorted order. If you're given three numbers, see, we are just comparing three numbers here. Okay, now let's go down this path, right? This path. If A1 is not less than A2, then what do we have? Then we'll compare, is A1 less than A3? Okay, let me just pull this here little more because I don't want to confuse you. So let me just pull this here, this part here. Okay. So my next comparison is going to be, is A1 less than A3. Just the way we filled up here. Okay, we'll also fill up here. I'm making this decision here. Either it's going to be yes or no. Right? Here, if it is yes, I already know the sorted order. Right? If this is yes, my sorted order is A2, A1 and A3. Right? Because I know this is no. Right? I know that A1 is not less than A2. A1 is not less than A2. and A1 is less than A3. Very simple. If the answer is no, then again I'll compare, is A2 less than A3? Okay, then I have again two possibilities. If it is yes or no. If it is yes, my ordering is going to be A2, A3 and A1. Here my ordering is going to be A3, A2 and A1. I hope I haven't messed this diagram, right? So, okay, probably I shouldn't put this in a box. Let me just avoid these circles here. Okay, so this is my sorted order. This is my sorted order. Now, look at this. What is this decision tree telling me? What is this binary decision tree telling me? Given any three numbers, given any three values of A1, A2, A3. Let's take an example, right? Let's say my A1, A2, A3 are 3, 1 and 2. First, I'll check this. Is A1 less than A2? This is my A1, this is my A2, this is my A3. Okay, let's avoid the same numbers. Let's just make the example more fun, right? Let's assume my A1 is 6, my A2 is 4, my A3 is 7, let's say. First, I'll go through this. Is A1 less than A2? A1 less than A2? No. So I come down this path. Look at this. I come down this path. No. Is A1 less than A3? Is A1 less than A3? Yes, that is true. Right? This is true. So what is my sorted order going to be? My sorted order is going to be A2, A1, A3. What is A2? 4. What is A1? 6. What is A3? 7. Yes, this is my sorted order. Right? So by just following this decision tree, okay, by just following this binary decision tree, it's called binary because at any stage, I can either go down this path or I can go down the other path. There are only two ways. That's why it's called binary. It is a decision tree because at every node here in the tree, we are making a decision whether to go in one direction or other direction. Right? So if you notice, there is something fun happening here. Okay. This is one way of ordering A1, A2, A3. This is the other way of ordering A1, A2, A3. This is the third way. This is the fourth way. This is the fifth way. And this is the sixth way. We saw here that if I have three numbers, the total number of ways in which I can arrange these numbers is 6. If you notice here, I have ordering 1, ordering 2, ordering 3, ordering 4, ordering 5 and ordering 6. So this binary decision tree, look at this binary decision tree has, so these nodes, see each of them is called a node, right? Each of them is a node. These nodes are called decision nodes because you're making a decision there. The nodes where there is no more decision to be made like this node where we have the final sorted order, these nodes are called leaf nodes. These nodes are called leaf nodes because there is nothing else below them. They are the end of the tree. Just like the end of a real tree. If you have a real tree, the end of a real tree is a leaf, right? So this is the end of the tree, nothing else below this, right? That's why these are called leaf nodes, right? If you notice the number of leaf nodes in this binary decision tree, the number of leaf nodes is equal to the number of ways I can arrange, the number of arrangements, right? Very simple, very, very cool logic, right? If you see, I'm just doing it with an example of 3, but you can do it with 10 elements also. Just that you'll not be able to draw it on a piece of paper. Now comes the other fun part. So the first important observation is that the number of leaf nodes is equal to the number of arrangements, which is nothing but n factorial. Okay, so let's write it down. The number of leaf nodes in the binary decision tree is equal to n factorial if the binary decision tree has n elements. If the binary decision tree is built to help us sort n elements. So what is this binary decision tree helping us? This binary decision tree is helping us sort n elements, using comparisons, right? These are all the possible, remember, these are all the possible comparisons that we are doing here. See, see, at the end of the day, I have all the possible sorted orders here, right? I have all the possible arrangements or orderings. right? So the binary decision tree helps me study how comparison sorting algorithms work. At the end of the day, that's what it helps me, right? So your binary decision tree is helping me sort n elements using comparisons. So you can use your binary decision tree as a mathematical model, as a mathematical abstract model. Okay, what is abstract? Basically a theoretical model, you can say, to study comparison sorts. Because doing this analysis on each of these comparison sorts is going to take you a lot of time, right? Is going to be very cumbersome. So instead of picking up one algorithm to study, we are saying any comparison sorting algorithm would be having a decision tree like this. At the end of the day, your binary decision tree is a mathematical model of all of your comparison sorting algorithms, right? And if you have n elements to be sorted, you can have n factorial arrangements. You can have n factorial arrangements, and the number of leaf nodes in your binary decision tree is going to be also n factorial, right? Because those are the maximum number of arrangements you can have. Now comes the fun problem. Okay, what is the height of this tree? Because look at this. Why am I even worried about the height of the tree? Why am I even, let's say h is the height of the tree. Why am I worried about height of the tree? The height of the tree, because at every height, at every level of the tree, okay, if you look at a tree like this, okay, let me draw a tree like this. Okay, imagine I have a tree like this, right? Imagine I have a tree like this. Okay, let's say all these are leaf nodes. This is called the level of a tree. All these are at one level, all these are at the second level, all these are at the third level, all these are at the fourth level, right? Very simple. Now, at each level of the tree, at each level of this binary tree, we are making a decision. So the height of the tree, the height h of the tree, okay, the height h of the tree tells us the number of comparisons. The height h of the tree tells us number of comparisons we make, number of comparisons we have to make, right, to sort an input array, right? Because we saw this example. If I'm given this input array, I could sort this input array using the binary decision tree. And the number of comparisons I will make, the maximum number of comparisons that I'll make is equal to the height of this tree, right? That is clear. Height of the tree is equal to the number of comparisons we have to make to sort. So the three interesting facts. This is the first fact. This is the second fact that we learned. This is the third fact that we learned. Now let's learn one more thing. Imagine if I have a tree like this, right? This is called the root node. This is called the root node. How many elements are present in the root node? Only one. Remember, this is a binary tree. These are called as binary decision trees that we have. Binary because at any stage there are only two possibilities. How many nodes are there at this stage? 2. How many nodes are there at this stage? Because each of this is breaking down into 2 more, I have 2 into 2, right? Which means I have 4 nodes here. Now again, this can be broken down into 2 more nodes because in each of these binary decision tree cases, I only have yes or no. So how many nodes can I have at this stage? Because at this stage I have 4 nodes. Here I can have only 2 into 2 into 2, which is 8. So this is called level 0 of a tree. This is called level 1. This is called level 2. This is called level 3. Right? So at level 0, you can have 2 power 0, which is equal to 1 node. At level 1, you can have 2 power 1, which is equal to 2 nodes. At level 2, you can have 2 power 2. This is nothing but 2 power 2, right? At level 3, you can have 2 power 3 nodes, right? So if you think about it, if the tree has height h, so this tree is said to have a height of 3. Okay, if you forget the root node, there are 3 levels, right, in this tree. So if you have a tree, if a binary decision tree, let's make it more specific. If a binary decision tree has height h, the maximum number of leaf nodes, that you can have, the maximum is 2 power h. You can't have more than this, right? So this is the other important fact. So we have these 3 facts and we have the 4th fact here. Okay, now let's see. Now if you take this decision tree, let's say we don't know the height of this decision tree and we want to find it. This height, so a decision tree of height h can have at most 2 power h leaf nodes. So for a binary decision tree like this, let's say I have my height, my maximum height. Of course, this is at a lower height than this, right? Because this is at level 2, this is at level 3, right? So let's say that what should be the height of the question that I'll ask is, what is the height of my binary decision tree? Binary decision tree that I'm building for sorting, right? Because I know that the number of leaf nodes, remember, I know that the number of leaf nodes is n factorial. So given that I know the number of leaf nodes, can I tell anything about the height of the tree? We know the relationship here, right? So using this relationship, that given a tree of height h, the maximum number of leaf nodes is 2 power h, I can write, because I know that I have n factorial leaf nodes, right? I know that I have n factorial leaf nodes in my binary decision tree that I built for sorting, which means your 2 power h is greater than or equal to n factorial if h is the height, if h is the height of the binary decision tree, the binary decision tree that we're building for sorting n elements. If h is the height, this is very, very important. If h is the height of the binary decision tree that we're building to sort n elements, of the binary decision tree to sort n elements, then this relationship holds, because the number of leaf nodes, remember, the maximum number of leaf nodes is 2 power h, right? So if you have these many leaf nodes, right, this relationship should hold. And if I take log on both sides, what happens? Because log is a monotonic function, right? Which means as x increases, log of x also increases. That's why it's called a monotonic function. So what can I do? If I take log on both sides, h is greater than or equal to log of n factorial, right? So we have to find what h is now. That's what we have to find, right? We know that there are at most, we know that for a binary decision tree, we have n factorial leaf nodes. We already know that because they are n factorial arrangements. Now the question that we have is, what should be the height? So we know now that height is greater than or equal to log of n factorial. Now we have already seen that log of n factorial, this is very interesting. We know that so this is one fact, right? Let's say this is fact 5. Okay, we already have this 5. There is one more very interesting relationship, which is log of n factorial is theta of n log n. Okay, we already know this. We have seen it in the growth of functions. So log of n factorial is theta of n log n. What does that mean? It means log of n factorial is also omega of n log n. What does the definition of theta mean? Theta basically means it's both omega and big O, right? So I'll use this now. I'll use this property to say that my h is omega of n log n. Okay, now comes the fun part. The moment I said this, what does this mean? Let's understand what this means in English. What this means is the height of my binary decision tree, right, which I'm using to sort the binary decision tree to sort n elements, its height is lower bounded by n log n. And what is the height? Height is nothing but the number of comparisons you have to make. Height is nothing but the number of comparisons. We have already seen this, right? Right? Height is nothing but the number of comparisons we have to make to sort these n elements. So from this I can say that the number of comparisons that I have to make is lower bounded by n log n. Right? So whatever sorting algorithm you use, as long as it is a comparison sorting algorithm, okay, that's the key here. as long as you are using a comparison sorting algorithm, you are bound by this fact that the worst case time complexity or the worst case number of comparisons you have to make is lower bounded by n log n. You cannot do better than n log n. That's what this means. And to do that, what did we do? We built a theoretical model of, or an abstract mathematical model of all comparison sorting algorithms using the binary decision tree. Okay, the flow of logic here is very simple. Okay, I'll just quickly revise it for you. If you're not followed through, please revise this. There's a very interesting flow of logic here. The first fact here is, given n numbers, you can arrange them or you can order them in n factorial ways. And if I build my binary decision tree as an abstract mathematical model of all comparison sorting algorithms, the number of leaf nodes is equal to n factorial, and each leaf node corresponds to an arrangement. And the height of this binary decision tree corresponds to the number of comparisons we have to make to sort. And we know that if you have a binary decision tree of height h, the maximum number of leaf nodes is 2 power h. And hence, we will come up with this inequality, right? Because this is the maximum number of leaf nodes that you can have for a binary decision tree of height h. So we just did some simple mathematical, we just took log on both sides, right? And this is what we got. And because we knew this property, that log of n factorial is theta of n log n, which basically means log of n factorial is omega of n log n, we said h, which is nothing but the height of the binary search tree to sort n elements, which is also nothing but the number of comparisons, is lower bounded by n log n. So what did we prove here with all of this mathematical machinery? We proved that you cannot have a comparison sorting algorithm that can do better than order of n log n. Does that mean we give up on this concept of linear time sorting algorithms? No. There are some hacks we'll do, but the only thing is you cannot have comparison based sorting algorithms. You can't keep comparing AI, AJ and build a mechanism which will do better than order of n log n. You can't do that because we have proven mathematically that it's not possible. So we'll come up with alternative approaches, okay, to come up with, to design a sorting algorithm that is linear time.